This is section 1.6 called Uncertainty in Measurement, and I do apologize because it does look a little busy, but the YouTube videos have a time limit. I wanted to make sure I hit it. Notice it's the same format. We've got the topic, we've got the assigned homework, and the numbers in bold are the things your TA should be covering when you are in recitation. So what's on this slide? Well, we want to first talk about the difference between exact numbers that are counted. Let's say if we have 12 eggs, we know that's a dozen. Those are counted numbers. Or if we were in our room, I would count the number of people in the front row. I'm very sad we're not there. Inexact numbers, they are going to be measured numbers, and they're going to come with the last digit that is estimated. All right, so that's one of the things that go into uncertainty. I use 3 different examples. The first one is a ruler. Notice we could have 1 digit after the decimal or 2 digits after the decimal, and we need to indicate what is our uncertainty. We could also be reading temperature on a thermometer, and this has been on midterm exams where there is a picture of a thermometer and you need to accurately tell us what the temperature is. The third thing is a balance where we would weigh something. A top loader, we say, has 2 digits after the decimal versus an analytical has 4. So we have a measurement of length, we have a measurement of temperature, and we have a measure of mass, or we commonly call it weight. All of this will be utilized as we go through the course. The next slide talks about the difference between precision and accuracy. Precision is how closely measurements agree with one another. Accuracy is how much they agree with what we call the correct or the true. Now, a correct is a mathematical calculation, but a true, that might be the number that you get when you repeat a measurement many, many times. So before we look at the example on the bottom, let's take a look at the slides. There is a bullseye dartboard where it says good accuracy, good precision. Notice all of them are right in the center. The second example says good precision. That's because all of the darts were thrown close to each other. As for the third, well, there's not much good we can say. They are not close to another, nor are they in the center. So you may get a word problem where you look at something and make a decision. You may also get what I would call a math problem, where someone would give you some numbers, you would find the average, and then you would be asked to determine which is more precise. So precise again is how close do they agree with one another? Well, that would be sample 2. 2.64, 2.58, 2.62, very, very close to the average. As for which is more accurate, if the true value is 2.52, you would compare it to the average, and that would be sample 1. Precision versus accuracy. Very important concept in class. Now this does look a little bit busy. No, really busy. It's significant figures. We have rules that we need to follow that are then used in protocol. And what it says is avoid ambiguity. When I look at this number, 92,500, I don't know how many significant figures there are. But if you look at my 3 different values with their numbers of sig figs, it tells me exactly how accurate the numbers are. So there are some rules. Any digit that is not 0 is significant. The number 112.1 has 4 significant figures. If I have zeros between non-zero digits, they are significant. 305 would have 3. 50.08 would have 4. That's rule number 2. Rule number 3, well, it makes no sense when you read it. Zeros to the left of the first non-zero digit are not significant. So if I look at that first number, 0023, the only significant figures are the 2 and the 3. The zeros are not significant. Don't get caught by the next example. Many zeros and a 1, this has only one significant figure, the number 1. But if I look back at 6.009, it really looks like rule number 2, and it has 4 significant figures. Practice until you are totally set as to how to use these rules. The fourth rule says zeros to the right of the last non-zero digit are significant if the number contains a decimal point. Best is to use an example. 1.200. There is our decimal. There are the zeros. This value has 4 significant figures. Again, back this up, see it again until you can confidently predict. Now, here's where we're going to use those rules. The first two refer to addition and subtraction. I suggest that you pretend you're back in grade school. Write the numbers just like you would if you were in, say, 3rd grade. Put a little line under the last digit of the problem so that you can readily track what the significant figures are. Why did I put it under the 3? Because it is in the second place to the right where the least significant number is. When I do subtraction, 143.29 minus 20.1, I come up with the value 123.19. Again, my least significant figure occupies the 10th place, so my actual value would be 123.2 with 4 significant figures. I should back up to the early example that had 5 significant figures. So those are the rules for addition and subtraction. When we do multiplication and division, there are a different set of rules. When I multiply 1.4, that has 2 significant figures, by 8.011, that has 4 significant figures, I need to choose the value with the smaller number of significant figures. So my calculator spews fast this number, but I need to have only 2 significant figures, so my correct answer is 11. For my second example, it is a division. I have 4 significant figures, 5 significant figures. My answer needs to have 4. Mathematically, it is 0.03782529, impressing you with digits. But I know my smaller number is 4 significant figures, so I know I need to truncate at that position. And looking at 4 significant figures, I need to round up. And so my answer is 0.03783 with 4 significant figures. Why did I round up? Well, if I look at the digit beyond the last desired place, if it's greater than 5 or equal to 5, I will round up. Again, spend some time on this page because here's what you see on your midterm exam. You will see what is called a mixed operation, and that will challenge you. If I have 6.266 minus 6.261, I come up with a subtraction of 0.005. So even though I can put these numbers in, I know my significant figure is at that position. My calculation gave me only 1 significant figure that I will carry out. So what I will do is I will say 0.005 divided by 522.0. 1 significant figure here, 4 significant figures here. My answer turns out to be 9.5785 times 10 to the minus 6, but I can only have one significant figure. And that means my correct answer is 1 times 10 to the minus 5. Again, that's the kind of question you're going to see on a midterm. The rules we shared teach you how to do it, but you need to take a step up. When you're doing multi-step calculations, please retain at least one extra digit through the entire calculation. Now, 2 slides from here, I will be doing these problems, and they came from office hours. We did the rules, but again, I say 2 right, both sig figs are on the right, 1 right and 1 left. That's what I mean by left of the decimal and right of the decimal. And then the killer problem. You know, what is end of chapter 150b? That's the one that really is very, very challenging. So again, we have some examples. They came from office hours where students were stuck, and so we made some things up to challenge. Okay, these practice midterm questions, again, they will be worked in the Zoom of lecture, and then answers will be shared afterwards.